Okay, hello everyone. This is the lecture for June 26, as I told you guys. Not in the country, I'm right now attending a conference as part of my PhD, but nonetheless, I've put a lot of effort on developing a material that I hope is going to really help you guys to complete assignment number one. The main point in here, we're going to continue to work with derivatives, and I'm going to show you guys different examples of how to approach the different derivatives. I'm going to start with something that is really similar to question number one on the assignment. And it's not that I'm bringing yet new concepts, but what I'm trying to provide is an approach of how to solve this particular problem. So let's assume, just to start, that what we have is this function, f of x equal x plus 2 over x. And what the problem says is that we're going to find the equations of the tangent sides of the curves. And this is the the function that the tangent lines have to be parallel to. So we're going to find the equations of the tangent lines to the curve that are parallel to this particular one. It's the same wording that you guys will find on the problem number one in the assignment. Just to get a little bit of a visual aid, as you guys know that I like to show you guys the visual portion to see if that helps you guys conceptualize what we're doing. The graph that you guys are seeing here is x plus 2 over x. So what we're trying to do is we're going to try to find parallel lines, tangent lines that are parallel to 2x plus y equal 5. Now, I understand that 2x plus y equal 5 is not the normal form that we have being y equal mx plus b, but that's nothing to worry about because we will transform it. The first thing that we need to do in order to solve this particular problem is to find the derivative of f of x equal x plus 2 over x. And as you guys can see, there's a component of x on the numerator, there's a component of x in the denominator, and what I'm going to propose is to apply the quotient rule. If you apply the quotient rule, as you guys remember, the quotient rule is going to be the numerator multiplied by the derivative of the denominator, which from x is going to be 1, minus the derivative of the numerator, and the derivative of the denominator, as you guys know, the derivative of 2 is going to be 0, and the derivative of x is going to be 1, multiplied by the denominator. And the denominator in this case is going to be x. All that divided by the denominator square, which gives us x plus 2 multiplied by 1 minus 1 multiplied by x over x squared. Just breaking the brackets that we have in here, then we get as a result x plus 2 minus x over x squared. I simply broke the brackets in here. X plus 2 is going to be x plus 2 if we multiply it by 1, and 1 by x is going to be x. Now, the situation in here is that I have x and negative x. That's going to cancel each other, and then as a result, I'm going to get 2 over x squared. As you guys remember, every time that we are trying to find the derivative of a particular function, we know that we're trying to find the rate of change or the slope of that particular function. That's why I'm referring to this 2 over x squared as the slope, because it's the derivative of the function that we were talking with. Now remember that what the problem is asking us is to find the tangent lines that are parallel to this particular function. And I told you guys at the very beginning that what we're going to do is we're going to transform this. So we're going to start with 2x minus y equal 5. But then we're going to transform that into just simply moving things around. As you guys can see, I brought the y to the other side and I brought the 5 to the other side. So the y was subtracting, now it's going to be positive. The 5 is positive in here, I'm going to send it to the other side, and now it's going to be negative. So as a result, I get that y is equal to 2x minus 5. And then, as you guys remember, we're talking about the form y equal mx plus b, what means that for this particular formula, the slope in there is going to be 2, because 2 is the value that is accompanying the x, right? So we have y equal mx plus b, y equal to x minus 5. Therefore, our slope in there is going to be 2. Why am I finding the two similar slopes? Because I'm gonna try to compare those two slopes and try to see if by having those two slopes I actually get to a formula of the lines that are tangent to that. So the first thing that I do is I take the 2 over x squared and I make it equal to 2. I'm trying to make equal the slopes from the formula that from the function that I need to be parallel with, and the main formula that I was working with. This will give me x squared. I bring the x squared up, I bring the 2 down, so it will be x squared 2 over 2. This is going to be equal to 1. And as you guys know, it is going to be either 1 or minus 1 that is going to give me this particular position. So that's what you guys see. We have two options because it was x squared. Then we have 1 and minus 1. Now what we're going to do, these are values that x can get. But then what I'm trying to figure it out is, well, that's the value on x, but then what is going to be the value on y, and what is going to be the formula that I can develop out of here. So I'm going to take these values of x, and I'm going to replace them on the main formula from which I'm trying to find the tangent lights of. So, sorry, the parallel tangent lights of. So what I do is, again, I bring it back to y equal to x minus 5, just by simply solving for y. And then I'm going to start replacing where x is the values that I got before. So as you guys can see on the left side of the screen, you guys are seeing that I'm replacing for 1, and on the right side, you guys are seeing that I'm replacing with minus 1. When I replace with 1, I simply solve for that particular solution, and I get that the set of coordinates for that particular point is going to be x being 1, y being negative 3. And if I do it for negative 1, I'm going to get x being negative 1 and y being negative 7. After I have this, I have the coordinates from which I can develop, or I can create the function that I needed to do. If you guys think about it, I don't know if you guys remember, but there's it's not the point slope formula, but it will get you to the point slope formula, and it's the idea of y minus y1 is going to be equal to m, that is going to be the slope, that multiplies x minus x1. In this particular case, I'm just going to first use the 1 minus 3, 1 being x, minus 3 being y. So y minus minus 3, because we bring the sign with us, minus minus 3 is going to be equal to m, that is going to be 2. And that 2, where is coming from, David? Well, that 2, if you guys remember, that was the slope that we got at the beginning, right? So that's where the 2 is coming from. And then we get x minus 1. And the 1 is coming from the coordinate 1 minus 3. I solve the brackets and I move things around because at the end of the day I want to solve for y. So negative negative 3 is going to be y plus 3 equal 2 multiplied by x is going to be 2x. 2 multiplied by minus 1 is going to be negative 2. This is going to give us that y is equal to 2x minus 2, and now I'm taking this plus 3 and I'm putting it on the other side of negative 3, so that's giving me y equal 2x minus 5. Now, you guys might be wondering, well, but what happened with the other portion? What happened with negative 1 and negative 7? Well, I also did it for negative 1 and negative 7. So if you guys look at this, we start with y minus y1, the same formula, equal to mx minus x1. Now, in terms of having the negative 3, what I'm having is negative 7 and negative 1. And what are the negative 7 and negative 1 common? Well, if you guys remember, that was the other set of coordinates that we were getting out of our previous one. So one set of coordinates was 1 and negative 3, and the other set of coordinates was negative 1 and negative 7. So I replace negative 7 on y and negative 1 on x. M, as I showed you guys earlier, is going to be 2 because of the solution that we did before. So negative negative 7 is going to be y plus 7. Negative negative 1 is going to be plus 1. And then I multiply 2 by x and 2 by minus 1. So then you get 2x plus 2 being equal to y plus 7. I solve for y, and then at the end of the day, I get y equal 2x plus 2 minus 7 would give me y equal 2x minus 5. Now, this is not to say that every single time that you guys solve for either of the coordinates that you guys are finding, remember, here we got y equal to x minus 5, and on the other side, we also go y equal to x minus 5. So this is not to say that every single time you guys will find the same solution for the problems that you guys are doing. Maybe there's other problems that I know that if you guys do this same process for the set of coordinates that you guys are going to find by comparing the function that you guys are trying to find the tangent lines that are parallel with, you guys are going to find different solutions. So it's not going to be, or maybe one is going to be y equal to x minus 5, but the other one can be a different function. So if when you guys are solving your assignment, you guys find that the solutions are not giving you the same function, don't worry about it. That means that there's more than one line that is going to be parallel, and that's all that matters. The next topic that I want to tell you guys about is implicit differentiation. And I'm going to assume that you guys are really familiar with derivative at this point, and all I want you guys to do is to don't worry about the idea of the implicit differentiation. It's a little bit abstract, and I'm going to try to explain it as simple as possible. And then you guys will let me know on Wednesday if you guys are having any trouble or not. So let's start with something simple. Let's assume that we have the formula being x squared plus y equal 2. Now, as you guys can see, this particular form is not solved for y. It's simply x squared plus y equal 2. If we were to solve for y, being y equal 2 minus x squared, you guys will know that the derivative of that will be 2 will be 0, and x squared will be 2x, so it will be y equal negative 2x. However, what we're doing here is a little different. With implicit differentiation, we find the derivative of each of the terms that you guys are working with. So let's go through it. For x squared, the derivative of x squared is going to be what? 2x. For y, the derivative of y is going to be y prime, which is dy over dt. It's just simply the derivative of y. And for 2, you guys know that the derivative of a constant is 0. After I have this, then I actually solve for y prime, and by solving for y prime, I get that y prime is equal to negative 2x, which will be the same answer that it will give me in the opposite manner. When do we use implicit differentiation? In the cases in which I'm going to give you guys a formula that contains y's as part of the same formula. So let's look at example number 2. Example number 2 says that you guys are going to have x squared minus 4xy plus y squared equal 4. I'm going to do it by parts. Implicit differentiation suggests that we're going to find the derivative of each of the terms. So I'll start for a simple one. X squared, derivative of x squared is going to be 2x. Okay. Now we get 4xy. The interesting part with 4xy is that we're going to treat 4xy as if it was the product rule. The product rule meaning that the first one is going to be 4x and the second one is going to be the y. As you guys remember the product rule says that we're going to have the first one, being 4x, multiplied by the derivative of the second one, and we agreed earlier that the derivative of y is going to be y prime, so that's why you guys see 4x being multiplied by y prime, plus the derivative of the first one, and you guys know that the derivative of 4x is 4, multiplied by the second one, and the second one is simply y. That's why we have 4x by y prime plus 4y. Now, here is the interesting part. The derivative of y squared is going to be 2y multiplied by y prime. And I know at this point you guys might be wondering why. What is going on? I'm going to finish with this. Derivative of a constant being 4 is going to be 0. And then now I'm going to focus on this particular one. How the derivative of y squared is going to be 2y y prime. Well, let me show you something, guys. Let's assume that you guys have g of y being y squared. A given formula completely apart from this context, but it's just to make the point of the example. So we have g of y being y squared. Let's assume that you guys are using the chain rule, being now we're gonna, instead of having y, I'm gonna have u. And if I have u, then you guys know that the derivative of u is gonna be 2u multiplied by u prime. All this is coming from the chain rule. So I replace my variable with a different variable, and then I'm trying to find the derivative of y on the terms of u. And then by doing so, you guys remember that this is gonna be as simple as bringing the exponent down, multiplied by the formula, negative 1 of the exponent, so 2 minus 1 is going to be 1, multiplied by the derivative of the inside. So in this case, it's going to be 2u multiplied by u prime. Then bringing y back into the formula, then I get, it's not going to be 2u, it's going to be 2y multiplied by y prime. Why y prime? Because it's the derivative of u. And since u is y, derivative of y is going to be y prime. That is why, now going back to where we started, you guys have the derivative of y squared is going to be equal to 2y multiplied by y prime. Derivative of y squared, that's the one that we were finding, is going to be equal to 2y by y prime. Don't worry, if it's not quite there yet, luckily this is a video, you guys can rewind it and then you guys can look it over again. I'm also having more examples of this particular concept, so you guys can clarify any particular questions that you guys might have about this. So going back, then I get that my entire formula is 2x minus 4xy prime plus 4y plus 2y prime. And what do we do at that point? Well, even though we are doing implicit differentiation, and even though it looks unusual that we have y and y prime as part of our solution, what we need to do is to solve for y prime. How do we solve for y prime? I'm just gonna keep the terms that actually contain y prime on one side and the terms that do not contain y prime in the other side. So as you guys can see, I simply destroyed these brackets because it was everything an addition or a subtraction, and then I kept 2y prime as the beginning, negative 4xy prime, negative 4xy prime, and then on the other side I took the negative 2x to the other side, and that's your negative 2x in here. Sorry, your positive 2x to the other side, and that's your negative 2x. And don't forget that the only importance of these brackets was to realize that this negative sign is going to affect these terms. So these terms, although it was looking as if it was positive 4y, in reality it was negative 4y because the negative was affecting what is happening inside the brackets. Then negative 4y, when I send it to the other side, is going to be positive 4y. Therefore, I get 2y prime plus 4xy prime minus 4y equal 4y minus 2x. Then I do common factor of y prime. So if I do common factor of y prime, what you guys will get as an answer is 2y minus 4x factor of y prime equal to 4y minus 2x. So if you guys can see, the 4y minus 2x stays exactly the same. I took factor of y prime, and then the 2y minus 4x that is going to be the result, I send it underneath to multiply, to divide. So the entire answer of this particular exercise is that y prime is going to be equal to 4y minus 2x divided by 2y minus 4x. Don't worry, I'm going to go over another example and see if it helps to clarify a little bit more. So let's look at this. We start with x to the power of 4 plus x squared, y squared, plus y to the power of 3 equal 5. Just as a suggestion, you guys know that if we have two variables, in this case are the two variables that we are actually interested on, being x squared and y squared, then this is going to be a product rule, or we will need to use the product rule in order to solve that particular one. If that's the case, then we get the derivative of the first term, that is going to be 4x, 4 minus 1 is going to be 3, so 4x to the power of 3. The product, and let's remember how the product rule works. The product rule goes, the first one, remember, I'm going to call x squared the first and y squared the second. If x squared is the first one, then I get x squared multiplied by the derivative of the second one. But remember that the derivative of the second one being y squared, if you guys remember what we did last time, the derivative of y squared, if we do the chain rule, is going to get you to 2u multiplied by u prime, which is going to be 2y multiplied by y prime. So in this case, we have x squared plus 2y y prime plus the derivative of the first one, and you guys know that the first one was x squared, so the derivative of the first one is going to be 2x, multiplied by the second one. And the second one in this case is going to be y squared. Now for the last one, it's really similar to what we did with y squared. So let's assume we have y to the power of 3. If we have y to the power of 3 and we change y by u, then we know that the derivative of that is going to be 3 u to the power of 2, because we use the power rule on there. But then since this is part of a bigger picture because we're using the chain rule, then you guys know that after you guys do the normal derivatives, you guys have to multiply by the derivative of the inside. That's why the derivative of y to the power of 3 is going to be 3y to the power of 2 multiplied by y prime. I know this may seem confusing, and what I've seen previously when I've taught this particular concept is that the students actually have a challenge only because the variable is y. If I change the variable to anything else, if I give you guys a p or an r as the variable, then you guys are more comfortable. Please do not let yourself get scared by having the y in there. Just because it's y doesn't mean that anything is different. Remember that we're always trying to find the derivative with respect to x, and therefore when we have y as our derivative, is like we're using the chain rule, we're changing it, and that's why we get these particular results. But as long as you guys are comfortable and as you guys are clear with the concept of the chain rule, then this should be understandable for you guys. Now, after I get to this particular point, I simply break the bracket. So the 4x3 is going to stay the 4x3. This is simply a multiplication between x squared and 2y y prime. So I just broke those brackets. 2x plus y squared is again just simply a multiplication, and then I get the 3y squared by y prime. As you guys remember from the previous example that I just showed you guys, the main point in here is to find or to solve for y prime. So if I want to solve for y prime, what I'm going to do is I'm going to take everything that is not y prime and I'm going to send it to the other side. So that's why you guys see that I'm first highlighting the 4x3, sending it to the other side, the 2xy squared, sending it to the other side. And then what I do is I take common factor of the y prime. So I'm going to get common factor of y prime of what? What was multiplying y prime? X squared multiplied by 2y. So that's the first one you guys see, x squared multiplied by 2y. On the other side, the y prime was multiplied by 3y squared. So that's the 3y squared. Now the other ones, I send them to the other side, so now it's not going to be 4x to the power of 3, it's going to be negative 4x to the power of 3 minus negative 2x y to the power of 2. Once I have it in this format, all I need to do is to send down as a denominator on the other side whatever is multiplying y prime. So y prime is going to be equal to negative 4x3 minus 2xy squared, which is the top, divided by what is on the bottom. Then in this case, it's going to be x squared 2y plus 3y squared. And that is the solution for that particular problem. Previously, when I've taught this particular concept, I know the main challenge is the y to the power of 3 or the y to the power of 2. Please be careful that when you guys see x and y in the same term and you guys are trying to find the derivative, you guys need to use the product rule. If it was x divided by y, then you guys will need to use the quotient rule. And then when you guys are trying to find the derivative of y, just apply the chain rule. and that will really solve a lot of what you guys are doing. Now let's look at this last example on implicit differentiation. And remember, guys, I'm right now developing this video, and you guys are having access to it. I also uploaded this PDF with all these exercises, so you guys can actually have access to it if you guys wanna write your notes on whatever you guys are seeing in this video. But also remember that these examples not only are similar to the ones that you guys are having on assignment number 1, but also will be really similar to the problems that I will be using for test number 2. You guys already know my methodology of teaching, and you guys know that I'm not going to come up with things that we haven't covered. I'm going to use the same format and the same concepts and exercises that we have covered in class or in the tutorials or in the assignments, and from there I'm going to give you guys, I'm going to take the exercises for the test. So let's look at this one. We have x squared over x plus y equal to y squared plus 1. And right from the get-go, I'm telling you guys that you should start by understanding that you guys are going to be using the quotient rule. Just focusing on the quotient rule, and that's just to the start. No, I haven't focused on y squared plus 1 yet. I'm just going to focus on this part and how you apply the quotient rule. If you're going to apply the quotient rule, numerator, denominator, two separate entities, and then I start. The derivative of the numerator, x squared, is going to be 2x, multiplied by the denominator being x plus y, minus the numerator, x squared, multiplied by the derivative of the denominator. What is the derivative of the denominator? Well, let's look at this. Derivative of x with respect to x, we know that is 1. And the derivative of y, and we know that the derivative of y, since there's no exponent or anything like that, is simply going to be y prime. That's why I get x squared, the numerator, multiplied by the derivative of the denominator, that in this case is going to be 1 plus y prime. All that divided by x plus y squared. That's just the derivative of x squared over x plus y by using the quotient rule. Not logarithmic differentiation yet, sorry guys. So here we are. Now we have 2x that multiplies x plus y minus x squared that multiplies 1 plus y prime all over x plus y squared. And on the other side, I just find the derivative of y squared plus 1. What is going to be the derivative of y squared plus 1? Derivative of a constant is going to be 0. And the derivative of y squared is going to be 2y. Remember, the exponent is going to come down normally as if it was the power rule. 2 minus 1 is going to be 1, so we don't have any exponent after that. So it's going to be 2y multiplied by the derivative of the inside, which is y prime. That's why you guys are seeing in here 2y, y prime. So we have the solution for the quotient rule equal to 2y, y prime. After we have that, then first I break the brackets that I have on the numerator. That meaning 2x by x is going to be 2x squared. 2x by y is going to be 2xy minus x squared by 1, that is going to be x squared, and x squared by y prime, that is going to be x squared y prime. Remember that the main point of these exercises is to be able to find or be able to solve for y prime. So what I'm going to do is I'm going to take the only term that actually has y prime and I'm going to bring it to the other side. What gives me that I now have 2x squared plus 2xy minus x squared equal to 2y, y prime multiplied x plus y squared. And I'm not expanding the x plus y squared because I just don't want to make it more complicated for you guys. This is the same term that we have up here, and then minus x squared multiplied by y prime. I factor y prime, then I get whatever was multiplying y prime, that it was 2y x plus y squared minus x squared. And then I get that y prime is going to be equal to 2x squared plus 2xy minus x squared. That's what I had in the other side. Divided, because this comes now to become the denominator, by 2y that multiplies x plus y squared minus, sorry, I'm missing the minus in here, minus x squared. David, could we expand the x plus y squared? Yeah, you guys know that that's going to be x squared plus 2xy plus y squared. But the main point in here is that you guys understand that the steps are always leading to solve for y prime. As long as you guys on the test or on the exam, you guys show me that you guys understand that implicit differentiation is trying to find for y prime in a different manner now by differentiating x and y's variables. That's what I'm looking for. The last topic that I want to tell you guys about today is logarithmic differentiation. And the only reason why I'm only talking about logarithmic differentiation, or that's the last topic that I want to talk about today, is because I don't want to overwhelm you guys with too many concepts before I see you. I understand that if you guys look at assignment number 1, there are 2 other concepts that will be missing. You guys will be able to cover at least 6 of the 8 questions that you guys have in there. The one concept is interest rate or exponential growth. And interest rate or exponential growth is simply a formula in which I would expect you guys to be using derivative per se, but I will expect you guys to know how to solve for an exponential when you guys have the variable with the exponent. And I'm going to show you guys that on Wednesday. The second one is the real life application of this implicit differentiation. And we just covered implicit differentiation, and if you guys want, there's more examples in the book, and I also uploaded a sheet with some examples of that. But the main point in here is that I want you guys to first be familiar with implicit differentiation, and then on Wednesday I can come in and I can clarify how this implicit differentiation actually makes sense when we talk about real life scenarios. Those are the only 2 topics that are missing, so you guys are able to complete assignment number 1. Remember that the deadline for assignment number 1 is July 5th, so even on Wednesday when I see you guys can come with any questions that you guys might have, and you guys still have a week to complete assignment number 1. Now, logarithmic differentiation. Remember that you guys also have access to your formula sheet on any of the tests or the exam that we're gonna conduct in the course. The main point in here is that I want you guys to have these formulas on your formula sheet. Why? Because those are the most important formulas when we talk about logarithmic differentiation. So when you have natural logarithm of a multiplication or order product being x plus y, x by y, sorry, this is going to be equal to the natural logarithm of x plus the natural logarithm of y. When you guys have natural logarithm of a division or a fraction being x over y, that's going to be the same as having natural logarithm of x minus natural logarithm of y. The last thing, natural logarithm of x to the power of something, that's going to be the same as having the something, which in this case was y, multiplied by the logarithm of x. These are rules, these are formulas for natural logarithms. And that's all you guys need at this particular moment to be able to solve logarithmic differentiations. So let me show you guys how we approach that. So let's assume that the problem is giving you, the first problem that you guys are having is y being equal to x squared plus 2 all over, all to the power of 2 multiplied by x4 plus 4 all to the power of 4. As you guys think, how do we find the differentiation of that? What you guys will be looking at is the idea of double chain rule. So you guys will have to like use x4 plus 4 as u, and then do it for x squared plus 2 also as a different variable, so it will be a double chain rule. Now, What the logarithmic differentiation says is that in cases where the functions are too complex, what you guys can do is you guys can find the natural logarithm on both sides. So natural logarithm on the left, natural logarithm on the right, and by doing so and then applying differentiation rules, then it will be easier for you guys to find the solution. So let me show you in this simple example here, and then there's another example that I want to go over with you guys. First, natural logarithm of y on one side and natural logarithm of x squared plus 2 all squared multiplied by x4 plus 4 all to the power of 4. Now, you guys remember that previously I showed you guys that when it's the natural logarithm of the product being x by y, that's the same as having natural logarithm of x plus natural logarithm of y. So what we're going to do in here is that now this is not going to be the natural logarithm of the product, but it's going to be natural logarithm of y equal to natural logarithm of x squared plus 2 to the power of 2 plus natural logarithm of x4 plus 4 to the power of 4. It's starting to look a little less complex. Now let's focus on what happened with natural logarithm. If you guys remember 2 weeks ago, if you guys remember 2 weeks ago, I gave you guys that the derivative of natural logarithm is going to be 1 over the variable, right? So what happens when we have natural logarithm of y? Because usually we work with x and we are always trying to find the derivative of x. So derivative of natural logarithm of x is going to be 1 over x. But in this case, since we have y, we need to apply the chain rule again. I'm going to apply it just by saying that y is going to be equal to u. And if y is equal to u, the natural logarithm of u, the derivative of that is going to be 1 over u. Remember, derivative of natural logarithm is going to be 1 over the variable of the natural logarithm. But in this case, since we are applying the chain rule, it's also multiplied by the derivative of the inside. Having said that, I bring the conversion back so that y was equal to u. And now instead of having 1 over u multiplied by u prime, what I'm going to have is 1 over y multiplied by y prime. Which means that the natural logarithm of y, the derivative of natural logarithm of y is going to be y prime over y. Let me do it again. I understand that this is the first time that we're working with this, so let me go through it one more time. We have the natural logarithm of y. We're trying to find what is the derivative of the natural logarithm of y, since we're trying to find the derivative with respect to x. We first apply the chain rule by, instead of having y, we're going to have u. And then by having natural logarithm of u, I find the derivative of natural logarithm of u. As you guys remember on the chain rule says that we're going to have the derivative multiplied by the derivative of the internal, which means that the derivative of natural logarithm is going to be 1 over the variable. So in this case, it's 1 over u. That's the derivative of the natural logarithm. You guys can look in your notes. Multiplied by the derivative of the inside. But the inside in this case is going to be whatever u is representing. So the derivative of u is going to be u prime. Now, when I bring this back to where I started with the chain rule, that it was y equal to u, what I'm going to get is 1 over y, because there's not u anymore, is y, multiplied by y prime, because it's not u anymore, is y. When I bring it in, then this is going to be equal to y prime over y. That's how the natural logarithm of y becomes y prime over y. Again, if you guys are having trouble, please just stop it right now. You guys can rewind it and then go over again. I would also recommend you guys that while you guys are looking at this, also take the time to do it yourself. Because when I'm explaining it and you guys are following on your computers, you guys might say, oh, this actually makes sense and I understand what David is saying. But only when you guys actually start practicing on your own is that you guys will realize if you guys are having challenges or not. And the main point in here is that I want to help you guys through those challenges. So if you guys come on Wednesday and tell me, David, this is what we're having trouble with, I will happily help you guys out. Now, not to say that I'm going to come on Wednesday and go over all this material all over again. No. I'm uploading this video and I'm going to know
how many of you guys watch it, because it's going to be on YouTube, and YouTube let me know how many views have been taken on the video. So please cover this material so we can complete the content before assignment number 1. Now, going back to where we started. So remember, let me just go back a little. Remember that we were up here. We were on natural logarithm of y equal to natural logarithm of x squared plus 2 all squared plus natural logarithm of x4 plus 4 all to the power of 4. I focus on natural logarithm of y because that was the first new thing that we have in there. And then we have agreed that the natural logarithm of y is y prime over y. But now, remember that this is part of a bigger picture. I started with natural logarithm of x squared plus 2 to the power of 2. But if you guys remember the natural logarithm rules that I showed you guys at the beginning, here they are. Natural logarithm rules also said that when you guys have natural logarithm of something to the power of something, then whatever is the power is going to come down to multiply the natural logarithm of the inside. In this case, let's check. We have natural logarithm of a function to the power of something. So what is going to happen is that this 2 is going to come down to multiply the natural logarithm of the inside. And that is exactly what I have on the next page. So you guys have natural logarithm of the inside, and whatever was before the exponent now is multiplying the function. It's the same for the next one. I have plus, it was natural logarithm of x to the power of 4 plus 4 all to the power of 4. Now we don't have a power, we just brought down 4 and we have the natural logarithm. And now,
So guys, sorry, I had to cut it and I had to restart it because I realized that I had a mistake. So when we were trying to do the natural logarithm of x squared plus 2, it will be the same as doing the chain rule. X squared plus 2 is going to be our u, and then we have natural logarithm of u. As you guys remember, natural logarithm of u is 1 over u multiplied by the derivative of the inside. In this case, the derivative of natural logarithm of x squared plus 2 is going to be 1 over x squared plus 2, remember, 1 over u, multiplied by the derivative of the inside. And what is the derivative of x squared plus 2? 2x. Now we do the same for the other one. So we have natural logarithm of x4 plus 4. And in this case, what we get is that the natural logarithm of x to the power of 4 plus 4 is going to be 1 over that. So 1 over x to the power of 4 plus 4, multiply for the derivative of the inside. So what is the derivative of x to the power of 4 plus 4? You guys know that the derivative of 4 is going to be a constant. So it's going to be 0, and then what you guys get is 4 multiplied by x to the power of 3. Now we get the multiplication for the values that you guys have on the outside, and then as a result, you guys ended up having that y prime is going to be equal to y that multiplies 4x, because remember, we multiply the outside for the inside, so 2 by 2x is going to be 4x divided by x squared plus 2, plus 4 by 4 is going to be 16, so it will be 16x to the power of 3 divided by x to the power of 4 plus 4. Let me show you one more example to just finalize this particular topic. So let's assume that we have y equal root square of x minus 1 over x to the power of 4 plus 1 to the power of 2. Sorry, the format is not showing it, but as you guys know, this is a PDF. So what the logarithmic differentiation will say is that we will apply logarithmic differentiation, or we will apply natural logarithms to both sides, right? So we'll start with natural logarithm of y and natural logarithm of the other side. You guys can also notice that what I did in here is I changed the x minus 1, the root square of x minus 1 to the other representation that is x minus 1 to the power of 1.5. Now, having said that, if you guys remember the rules of logarithmic differentiation, we get that when you guys have logarithm of a fraction or a division,
then that is the same as having natural logarithm of the first minus natural logarithm of the second one. In this case, meaning natural logarithm of the numerator minus natural logarithm of the denominator. Now, going back to our previous example, then what we get is that if we have natural logarithm of x minus 1 to the power of 1.5 divided by x to the power of 4 plus 1 to the power of 2, this is going to be the same as having natural logarithm of y equal to natural logarithm of x minus 1 to the power of 1.5 minus, as you guys can see, we don't have the denominator anymore. Now it's going to be a subtraction. Minus natural logarithm of x to the power of 4 plus 1 to the power of 2. Now, using again the natural logarithms rules, then you guys know the natural logarithm of x to the power of y is going to be y multiplied by natural logarithm of x. Having said that, then what you guys ended up having is natural logarithm of y, that we already explained what it was, y prime divided by y. And if you guys don't remember, you guys can scroll through the PDF and double check how we got from natural logarithm of y to y prime over y. And then using the logarithmic differentiations, you guys know that the 1.5 is going to come down to multiply the function. The same with the 2 is going to come down to multiply the function. So we get y prime over y equal to 1 over 2 natural logarithm of x minus 1 minus 2 that multiplies the natural logarithm of x to the power of 4 plus 1. Once we have that, I'm solving for y prime, so I'm bringing the y to the other side. And then remember that the differentiation or the derivative of natural logarithm of x minus 1, it will be applying chain rule. X minus 1 is going to go to the division. Remember, 1 over u multiplied by u prime. 1 over u multiplied by u prime. So in this case, it's going to be 1 over x minus 1. Derivative of x minus 1, remember, derivative of 1 is a constant, is 0. Derivative of x is going to be 1. So you guys get 1 over x minus 1 that multiplies the 1.5. That's where the 1.5 is coming. And now on the other side, we get 2 that multiplies natural logarithm of x4 plus 1. So again, chain rule, x4 plus 1, your u. So 1 over x4 plus 1, because it's your u, multiplied by the derivative of this. But what is this? This is x4 plus 1. 1, a constant, derivative 0. X to the power of 4 is normal power rule, so this is going to be 4x to the power of 3. Therefore, the derivative of natural logarithm of x4 plus 1 is going to be 1 over x4 plus 1 multiplied by the derivative of the inside, that is 4x to the power of 3. All this multiplied by the previous 2, what will lead us to y, which is the factor, y prime equal to y, that is the factor, then multiplies 1 over 2, I simply multiply the 1.5 by everything I have in here, so it's going to be 1 over 2 that multiplies x minus 1, and I did the same in here. It's going to be negative because it was a fraction when we started, and it's going to be 2 by 4, it's going to be 8, ax to the power of 3 over x4 plus 1. Guys, this is all that I have for today. So in this video, I've covered how to find the parallel lines to the tangent of a particular formula. I've also explained you guys implicit differentiation, and I've also covered logarithmic differentiation. Please watch this video, try these exercises on your own, try to figure it out where you guys are having trouble. If you guys have any question, please do not hesitate on contact me, and I will see you guys on Wednesday to continue with these topics. Thanks a lot.